now we will go to the fifth and final lecture of week 4 of this course. Okay. In this lecture, I will summarize what we learnt in week 4 and then do one practice problem. So week 4 lecture 5 we will have a summary of week 4 and practice problems. Okay. So what did we learn in week 4? We learnt about translational symmetries and then we learnt about notations for symmetry. So first we looked at how to view translation as a symmetry operation, okay, especially with respect to lattice translations. Okay. Then we learnt about screw axis, we learnt about glide planes, and then finally I talked about the role of symmetry as to why we need symmetry, and then we learnt we saw some notations for symmetry elements. Okay. Now so all this actually concludes the 2-week discussion on symmetries. Okay. Now let us look at one example. Okay. Here you are asked to identify all the translational symmetries of a monatomic HCP crystal, and then you are asked to depict the planar structure of an HCP structure showing a HCP crystal showing all symmetries. So you should keep in mind that HCP is not a Bravais lattice. So HCP is not a Bravais lattice, and it consists of 2 interpenetrating hexagonal lattices. Okay, so what does HCP look like? Okay, I will just show you here. So if you have, let us say, in the plane of the paper, okay, you can have one hexagonal lattice. Okay, that will be in this manner. Okay, so this would be a hexagonal lattice. Okay, and this you can imagine this you can say it is at z equal to 0. Okay, and it will be at z equal to 0 and at z equal to 1 and so on. The other hexagonal lattice, okay, which will be at z equal to half, will be will be located this way. So this is at z equal to half. So it keeps alternating this way, and it forms an AB type stacking. So later on we will learn about stacking of crystals, and this corresponds to a AB stacking. That means the z equal to 0 layer, okay, is followed by the z equal to half layer, and then the third layer is on top of z equal to 0. So the atoms are stacked in layers of this form AB. Okay. Now how do we show what are the translational symmetries of this HCP crystal? Okay. Now let us look at the glide planes. Okay. Now let us again show the before we look at the glide planes, it is instructive to think what would be a suitable unit cell for this HCP lattice. Okay. Now typically the unit cell is chosen in this manner. So you choose a cell of this way. Okay. So you choose A and B, and C is perpendicular to the screen. Okay. So that is a typical choice of unit cell. Okay. And now let me show that unit cell here. So, this is at z equal to 0, and then you have at z equal to half, you have one atom that is located right here. So, essentially there are two atoms in this unit cell. Okay, so if you look at this whole cell, you see atoms at the corners, and the net contribution of all those atoms is just one atom, and then you see one inside the cell. Now, if you take the HCP cell, okay, and let me expand it a little bit, okay, just to illustrate the point. Now, what you can see when you expand it is the following, that each of the planes has a six-fold symmetry. So, so each of the individual planes by themselves, okay, they have this six-fold rotation axis. Okay, so if I just connect these just for ease of visualization. Okay, now if you take this z equal to 0 plane, it is a hexagonal lattice. So, it has a six-fold axis of rotation. However, since it is interpenetrating with this z equal to half, okay, there is not a so that does not act as a six-fold axis of rotation for the HCP lattice. Okay. The other thing that is slightly, let me now show the unit cell that we wanted to consider. So, we wanted to consider one unit of this as our unit cell. Okay. This is the unit cell where A, B and C is defined perpendicular to the screen. Okay. Now, one of the things that is not obvious with this unit cell is the inversion symmetry of the HCP lattice. Okay. Now, actually HCP lattice has an inversion symmetry, okay, and that inversion is with respect to a point that is right here, that is halfway between this corner point and this point inside the cell. So, this is a point of inversion. Okay. And now, sometimes it is convenient to show the symmetries using this inversion point. Okay. Now, this inversion point is located at z equal to 1 by 4, okay, and at the appropriate coordinates of A and B. Okay, but it is located at z equal to 1 by 4. Okay. Now to show the symmetries of often what is done is to show the symmetries with respect to this inversion point. Okay, taking we want to have a cell, okay, which actually captures this inversion center. Okay. And there are several ways to do that. Okay, I should also mention that there would be other inversion centers. So, for example, there would be one here. All these are at z equal to 1/4, and similarly there will be one at z equal to 3 by 4. Okay. And there would be inversion centers here. sometimes we choose unit cells so that they capture this inversion, this center of inversion is naturally captured. Okay. And so, for example, you might choose a unit cell that is in this form. Let me use. So, if you choose this, for example, as a unit cell, okay, where it starts from z equal to 1 by 4 and goes 1 unit up. Okay. Now, you can see that all these are inversion centers. Okay. So, all these become inversion centers. Okay. And this is often now this cell, this unit cell has inversion symmetry, because there is a point of inversion right in the middle of this cell. So, just as z equal to 1 by 4, there is also a similar point directly above it at z equal to 3 by 4. Okay, there will also be a point directly above it at z equal to 3 by 4. So, that the point at z equal to 3 by 4 will be at the center of this cell. So, a cell that is taken with these points has an inversion center in middle of cell. Okay. So, right in the center of this point. Okay. So, this point will be a point of inversion. Okay. So, let me draw this cell here. So, what it will look like. Okay. So, you will have points. And you have, so this is at z equal to 0 and half and 1. Okay, so this is z equal to 0 and you have a point of inversion at z equal to half. Well, okay, so I'll just write this as half. Okay. So, these points are at z equal to 0, these are inversion points. Now, the question is, in this the atoms are not located at the corners. Okay, so the atoms are located somewhere here. Okay, and the other atom is okay, and with respect to this cell. Okay, this atom, okay, so this was located at half in the original cell. In this cell, since it is translated by, it is already raised by 1/4. Okay, this atom will be located at 1 by 4, and this atom will be located at 3 by 4. So, maybe I'll use a different color. I'll use the blue color. This is at 3 by 4. So, this is the same unit cell. Now it has two atoms, okay, 2 points that are inside. Okay, the corners, there are no points at the corners. Okay, and this is what we'll use to show the symmetries. Okay, let me show the other inversion centers. There are also inversion centers here, and here, and here. Okay, so I should mention that there will also be an inversion center right here and right here in this cell. Okay, so these are the inversion centers in this unit cell, and you can already see that also you can easily see that the point at the center is a point of inversion, because if you invert about this lattice point at 1 by this purple lattice point will go to the blue lattice point and vice versa. Okay. Okay. Now we can show the other symmetry operations. Okay. So, so since you have this inversion, you will have in addition to this, now we'll first show the glide planes. Okay. now there is a glide plane, okay, that is, so if you take a glide plane that is yeah, let me extend this cell, then the glide plane will become clear. So, we will extend it here. Okay. And this point will come right here. And you will have this point that is right here. Okay. Now, now the first thing that you will see is that if you look at a plane passing through this 1 by 4, passing through z equal to 1 by 4. Okay. So, if you look at a plane in the in the plane of paper, okay, passing through z equal to 1 by 4. Okay, this is a plane of reflection. So it is parallel to the screen, but at a height of z equal to 1 by 4. Okay, so that is a plane of reflection, and that is fairly easy to see. Okay. The next thing that you will see is that there is a glide plane, okay, that contains the A and C axis, okay, and this will reflect the. So, now there will be several glide planes in this crystal and in this lattice, and let me show some of them. So, there will be a glide plane here, okay, and this in this. So if you reflect about this plane, okay, and you can translate well, will be seen more clearly if I extend this cell. So, let me extend it in this direction. Okay. So, you can see that if you reflect this point and translate along this line, okay, if you reflect about this plane, okay, and well okay, so if you reflect about this and translate along this line, okay, you will end up with this point. Okay. Similarly, if I okay, so there's a glide plane in this direction. There is similarly there will also be a glide plane this way. Okay, glide reflection. So you can see that if you reflect this point will come directly here. Okay, and then you can do a translation to get to this point. Or so if you reflect about this, you will end up here, and then you translate it along this line, you will get to this point. So these are some of the glide planes. Okay. Now, what are the other? Now, again just by symmetry of this unit, you will have glide planes also here. Okay. There are several other glide planes in this HCP lattice. Okay. I will show some of these. Okay. There is a diagonal glide plane. Okay. There is a diagonal glide plane that is located here. Okay. And the symbol for a diagonal glide plane is a line and a dash. Okay. So, this is a diagonal glide. So, N glide plane. Okay. this is a C glide plane, and so on. You can show several other glide planes that are symmetrically reflected in this. So if there is one here, there will also be one in this direction. Okay. So, these are the glide planes in this diamond cubic lattice. Okay. Now, what about the screw axis? Okay. Now, it turns out that you can again work it out with this unit cell that we looked at. So, with this invertible unit cell, okay, these are all centers of inversion, and you have your two lattice points. One was located here, the other was located here. This was at 1/4 and this was at 3/4. Okay. Now, the screw axis in this there is a 6-fold screw axis that is located here. Okay. And we want to emphasize that there is also an inversion center here in addition to the 6-fold screw axis. So, we will draw it this way, and similarly it will be at all these corners. So, this is a 6-3 axis, 6-3 screw axis. So, 3 is so that means you rotate it by 30 degrees. Okay. Rotate by 30 degrees and translate by half of the unit cell. So, if you rotate the crystal about this, you can easily verify that it is indeed a screw axis. Okay. There are additional screw axes. Okay. So, for example, there is a 2-fold screw axis here, okay, right at the center, and again we want to leave the center of inversion. We want to emphasize that this point is also a center of an inversion center, and you have other 2-fold screw axis here. So, these are all 2-1 axis. Okay. So, these are the screw axis for the diamond, okay, for the diamond cubic. So, the highest order screw axis is the 6-3 screw axis, okay, but there are also these 2-1 screw axis that are there in diamond in the HCP, sorry. So, the highest screw axis for the HCP is this 6-3 screw axis. Okay. Now, let us put it all together and let us do a planar representation of the various symmetries of this HCP lattice. Okay. We already saw, we have already seen a lot of the symmetry elements, and we will just put all of it together. And there is also and we had our 6-3 screw axis, notice that there is a 6-3 screw axis and an inversion, okay, and therefore you have this little hole in the middle. So we are showing both the 6-3 axis and the inversion center at this point. Similarly, we will show both the 2-1 screw axis and the inversion center at this point. So it's a 2-1 screw axis with an inversion. Okay, so you have the 6-3 and the 2-1. Okay, now let's show the other glide planes. Okay, I'm not going to discuss this in too much detail. Okay, first I'll show the mirrors. So the mirrors, the in plane, the mirrors that are perpendicular to the screen are and as is the usual convention, you only show the two-fold mirrors that are perpendicular to the screen. Okay, so all these are mirror reflections. Okay, now there are some other interesting symmetries that are there. Okay, there is a 6-bar. There's a 6-bar axis right here, and 6-bar, this is the symbol for 6-bar. Okay, similarly, there's a 6-bar right here. So this is a symbol for a 6-bar. Okay, so and then we'll show all the other. So these solid lines are the two-fold reflections. Okay, these are the screws. Okay, and we have shown a 6-bar. Okay, there are other mirrors. Okay, which I'll just which I will emphasize. So for example, there's a mirror here, okay, which is actually an in plane glide. And so on. You can extend it again to the entire. You'll have one here. Okay, so this is a planar representation of not all the symmetries, but at least a significant fraction of the symmetries of the HCP cubic lattice. So HCP lattice has a total of 24 symmetry elements. Okay. Now the asymmetric unit of this corresponds to just one. It corresponds to just one atom. Okay. So with these 24 symmetry operations, you can generate the entire HCP crystal. Okay. So it has a total of 24 symmetry elements. Okay. And these are the unique symmetry elements. Okay, unique in the sense that you only apply them to you only look at those in the asymmetric unit. So the asymmetric unit, for instance, would look like this would be an example of an asymmetric unit, because it cannot be the entire cell. Okay, so it would be, for example, it would be this. Okay, because the entire cell contains two atoms. or 2 points, okay, the asymmetric units will contain only 1 point. Okay, so it will be half of this, half of the entire unit cell. Okay, so with this I will conclude week 4 of this course. Okay, so in this week we have looked at translational symmetries, and we have seen how to represent symmetries on a piece of paper or a screen. Okay, now I have not done these in too much detail. My basic idea was I wanted to give you an idea of some of these things. Okay, and these are things that you might see in various books or various websites, and so it is good to know them in general. Okay. However, we won't be discussing too much, we won't be working out too many problems in this area of symmetry and crystallography. Okay, our goal is to learn how to describe crystals, and then what is the chemistry of these crystals. So with this I will conclude week 4. Thank you.